Okay, now moving on to standing waves in tubes. We've already had a look then at the examples of standing waves formed in strings. It also could apply to things like microwaves, which we will be looking at practically. They are transverse standing waves. We're now talking about standing waves then that are longitudinal. Not quite so easy to visualize as perhaps a transverse wave. So sound is a classic example of the type of standing wave or stationary wave that we're getting here. So when a sound wave here travels along a tube, if it gets to the end of the tube and the tube is sealed, it reaches the end, the wave energy is reflected back into the tube. And then the superposition of the original sound waves and the sound waves that are reflected back once again produces a stationary wave. Point to note, if that is our tube, at this end here, if it is sealed, if it's a closed end, the air molecules can't move, so we automatically always have a node at a closed end, and correspondingly, at an open end up here, the air molecules are free to move, so we always have an antinode at the open end. So this has to be a node, this has to be an antinode, and that constrains the particular frequencies that we're actually going to get out of this tube. All right, so here's the most simple situation then. We've got our node down here then at our closed end and our antinode again at our open end. The simplest form of stationary wave that we would get would be one that is effectively 1/4 of a wavelength long, or lambda divided by 4. And that's represented by this line, these lines here. Now we have to be a little bit careful in interpreting those lines, because that makes us start to think about a transverse wave. It certainly looks like a transverse wave, but we're actually talking about a longitudinal wave. So just sketching a center line down the middle there, what this really is giving us is a graph of displacement against position. So if we take distances here, the longer these arrows, then the greater the displacement we're going to have for particles away from their equilibrium position. Right down here at the node, there is no displacement. So over on the left here, we should be able to draw in what the particles are actually doing, as opposed to this thing over here, which is really a graphical representation of what's going on. So at this end here, particles can't do anything. At this end here, at our antinode, the particles are oscillating, but they're not oscillating sideways, they're oscillating longitudinally. So the length of that arrow there would be what we take off the graph there. That's what that is telling us, the amplitude of the oscillation of the particles. Further down in here, where maybe if we come across from there, the arrows are shorter, then the amplitude of oscillation is less. If we come across here somewhere, the arrows are smaller again, and so the amplitude of oscillation is once again smaller. I'll just clear this off a bit. It's become a little bit messy there. What I want you to put in your notes then would be the two diagrams. The one on the right hand side here, just showing the graphical representation, and take note of the fact that it's a graphical representation, and then you could complete this diagram on the left, maybe a bit more tidily than what I've done there. Something like this then. Particle motion, particle motion, particle motion. So the amplitude of this motion getting less as we move closer to the node there. All right, taking things a step further then, the most simple form of stationary wave that we're going to get then is this one on the left-hand side, where the wave where the length of the tube is equal to lambda divided by 4. It's a quarter of a wavelength. So that's where we get this idea then that the wavelength must equal 4L. Now, when we look at the next possibility, because we have to have a node there and we have to have an antinode there, we can't have the possibility that L equals lambda over 2. Because if you had L equals lambda over 2, you'd be saying something like that, that you got a node there and you got a node there. Impossible. So that one doesn't occur in this type of situation with an open pipe. So therefore, what we've got in this situation, then that's effectively here, is 3/4 of a wavelength, so that the length of the tube is equal to 3 lambda over 4, and that's just rearranging that. That's where we get the wavelength down there is 4/3 of L. And then the next possibility is that the length of the tube is equal to, well, there is effectively 1 lambda plus another quarter. So 5 lambda over 4, 1 1/4 wavelengths present there, from which when we rearrange it, we get the wavelength as being 4L over 5. The frequencies that are generated then are this first frequency. We can't get twice the frequency, so we next get 3 times the frequency, we next get 5 times the frequency. So all we have present then is the fundamental over here. We don't get the second harmonic, we get the third harmonic here, we get the fifth harmonic here. So with a pipe that is closed at one end, we only get the odd harmonics being produced. It's impossible to produce an even multiple of the fundamental frequency. Open tube, though, is different. If it's open at both ends, we still get stationary waves. This time is a strange sort of idea, but it's almost as though it is really that the sound waves are bouncing off the open end here and coming back. And we saw that with the wave machine in class, that we could send have an open end and still be able to set up a stationary wave there. All right, so this time we're constrained to have antinode at this end, antinode at this end, and therefore there must be a node in the middle. So we get our fundamental frequency, this time that the wavelength, or let's say that L is equal to lambda divided by 2. And then here we've got a full wavelength, so L is equal to lambda, and here we've now got 1 1.5 wavelengths, so that's 3 lambda over 2, and from each of those things we get these statements down here about what the wavelength is equal to. This time we do get the fundamental, we do get the second harmonic, we do get the third harmonic, so the even harmonics are also present there. Now I should just say that I think this diagram that's on this page and the previous diagram, that was that one there without my scribbling all over it, should be put into your notes there. Okay, either copy them out or print them off. It's up to you how you deal with that. Comparing the two tubes, that's the closed-end tube and the open-end tube, it's interesting to note then that the fundamental frequencies are different. The same length tube, in one case open, in the other case closed, will give a different frequency, and we'll just illustrate that in a moment. And as we've already seen then, the overtones are different multiples of the fundamental there. All right, so this just illustrates sort of a bit of a summary diagram here. You don't need to write this one down. I'd say if you've done the previous diagrams, that's fine. But this idea of looking at the frequencies we get, we're saying here we get frequency F1. We're saying here we get frequency F1 from an open tube here and from a closed tube here. Those two frequencies are not the same. If the tubes are the same length, we see that the wavelength here is 2L. The wavelength here is twice as long, 4L. If we've got double the wavelength, V equals F lambda, V being a constant. If we have the wavelength, twice what it is up here, then the frequency should correspondingly be half. All right, so this frequency here is half of the frequency up here, or this frequency up here is 2 times the frequency produced down there. Okay, a series of examples now, which I want you to copy into your notes, and I want you to work through and do them. And if you have any difficulties in answering the questions, please let us know, and we can go through them in class. All right, let's have it. I'll have a read of it, and let's just see if there's anything we need to do, just to maybe give you a few clues. Eh? In a resonance tube, then experiment, we've got a tuning fork. Okay, doing the same job as the speaker effectively, 256 hertz, held over the open end. We get resonance. We hear that loud sound. That's called resonance at the top of the tube, and we're 31 centimeters. Here it is here, above the top of the tube. So that must correspond to the first possibility, where the length of the tube is 1/4 of a wavelength. You're asked, and you're also told that you get the thing again at 96 centimeters, this time where it must be 3/4 of a wavelength. And you're asked to determine the speed of sound in the tube and the distance above the open end of the tube of the antinode. We'll worry about that one in a moment, eh? Let's have a look. I've just sort of got a miniature version of it here. So the speed of sound, V equals F lambda. So we've got the frequency, 256 hertz. We need to get lambda. So we've got 31 centimeters and we've got 96 centimeters. Now the 31 is not actually 1/4 of the wavelength. If you have a look up here, see this in the part of the diagram? There is this thing called end effect. Now, in reality, with an open-ended tube, the antinode is not actually exactly at the end of the tube. It's slightly beyond the end. And again, you'll see that it's slightly beyond the end, whereas the measurements are taken to the end of the tube. Okay, have a think about that. I think we'll actually go through that and discuss how we deal with the problem in class rather than me trying to say too much more about it now. So have a go, see if you can nut out how you're going to solve that problem, and if not, we will look at it together. Okay, second example, air blown over a closed tube 1.2 centimeters long. That's quite short. Fundamental frequency set up in the tube, assuming antinode is formed. This time we're going to make the assumption that it is formed at the top of the tube rather than beyond the tube, and we've got the speed of sound. This one here to me looks to be a lot simpler than the previous one. Okay, and you've got to calculate the fundamental frequency. So I think you should be able to do that one yourself without any further direction. Third example. Sound wave, closed tube, fundamental frequency 315 hertz. Speed of sound in the air 340 meters per second. Antinode formed at the open end of the tube, situated level with the top of the tube. So we're ignoring end effect again. All right, so you've got to work out the length of the tube. I think you should be able to do that. The length of the open tube that would have the same fundamental frequency. So first of all, the length of the tube if it's closed, and then if it had have been open, one that's going to give you that same frequency. You're going to have to change the length of the tube. And then both tubes sound the same fundamental frequency. How is this possible to distinguish between, state how it's possible to distinguish between the two notes? So open tube, closed tube, both giving the same fundamental frequency. How could you figure out which is which? I assume that would be with your eyes closed, because if you open your eyes, you'd see which one is closed. Anyway, have a think about that one too, please.